I would like to continue with the previous discussion on discrete probability distributions. So with an example, so we have an example here for the DiCarlo Motor store. So basically it's a store in Saratoga, New York, and over 300 days they have this historical data where there are 54 days with no automobiles. Then there's 117 days with one automobile sold, and then there's 72 days with two automobiles sold, 42 days with three, and so on and so forth. So if you're considering the experiment of selecting a day of operations at DiCarlo Motors, and you define a random variable x of interest to determine the number of automobiles that would be sold in a day. So you basically, from our data, if we convert this data into a frequency, if you convert this data into a frequency table and you compute the probabilities, we come up with this table where x is the number of cars sold. So we say for how many days? So for 54 days, so that represents a 0.18. So this the proportion. The probability density for this event. So this event of no cars being sold happened 0.18% of the time. Yeah. So these are the probabilities that we know from our historical data. So if we take those probabilities, we could basically create a probability function. So a probability function. So we said in a discrete probability distribution, a probability function is basically some function, some f of x, that can give us the probability of x happening. Yeah, it's some f of x which can give us the probability that x happened. So in a discrete probability distribution, given some x, we can actually know exactly the probability of the x. So in our case, if you are dealing with the historical data, our f of x is basically some step function whereby you have let me just just a minute. So basically I want to have a big bracket. Okay, so brackets, I want a one-sided bracket, single bracket. Yeah, so I want a one-sided bracket. So I want one of these, maybe, so you want to have something like that. So f of x is going to be 0.18. So it's basically a bunch of if statements in here. If 0, then it's going to be something else. So it's going to be something else. 0.39, 0.39. If 1, then it's going to be 0.24. If 2, 0.24. If so in this case you have what you call a step function. Yeah? So it's not very elegant, but it conveys what I'm trying to say. So basically, if you have these kinds, if you have described the distribution, then it means that you can directly compute the probability of a particular. It means you can directly compute the probability of a certain event happening. You can actually directly compute the probability of a certain event happening given some information about x. Yeah, given some information about the random variable. Given the random variable, you can actually compute the probability. So we are going to do a lot of this in a short while. So this is for the DiCarlo Motor experiment. But in general, if you move more generally speaking, there's a few discrete probability distributions that are very common in application, that are very commonly applied, that are very useful. And the first one that you're going to consider is what you call a discrete uniform probability function. So the discrete uniform probability function basically is will give you this. If the f of x is basically 1 over n, where n is the number of values, where n is the number is the number of values that the random variable may assume. So you have a uniform distribution when you assume when you make the assumption that that all events are equally likely. So if you have a situation in which all events are equally likely, if I take you back to the coin example, it is a classical example of a uniform probability distribution, because if you have a single try, for instance, for a single try, then n is going to be 2, because you have 2 possible values, and the probability for an unbiased coin, if you're dealing with an unbiased coin, is going to be 1 over 2. If you have 2 attempts, then it's going to be 1 over 4. So the events equally share out the probability in the sample space, and that's what we call a discrete uniform probability function. We have a small exercise here. So what do you think this is? So here you have an f of x, and f of x is 0.2 where x is 20. It is 0.15 when x is 25. It is 0.25 when x is 30, and it is 0.4 when x is 35. So do you think that this is actually a uniform probability distribution? So this is actually from the book. So the answer is at the end of the book. So this is homework for you that you can go and figure out. But remember, we said in the uniform, discrete uniform probability function and a discrete uniform probability distribution, the probability is given by 1 over n, where n is the number of, where n is the size of the sample space, the number of possible values that the random variable can actually take on. And for the expected value is quite straightforward to compute. So the expected value for a discrete random distribution is basically you can use this. You can call it E of x or mu, but basically, so both notations are used widely, but it's given by this summation of x of f of x. If you go back to our Monte Carlo example, or the Carlo Motors example, I'll just show you how to compute this in a bit with Excel. So basically, remember, in this case, x, the random variable that we are tracking, x is actually the number of cars that are bought in a given day. It is the number of cars that are being bought in a day. Let me just increase the zoom a bit. So we say when x is 0, we have 0, 1, 2, 3, 4, 5. Yeah. So we have 0, 1, 2, 3, 4, and 5. And based on the frequencies that we had, because we got these frequencies from this description. So we get these frequencies from this description over 300 days. Yeah. So we get it over 300 days, and then we use the frequency distribution as a probability distribution. We convert it directly to probabilities. So we have a 0.8. So the frequency was 0.18. Yeah. So frequencies are 0.18. Then we have 0.39, 0.24, 0.14, 0.04, and finally we have 0.01. So this is our so that is our data. So we're basically saying that the probability is going to be, the summation of this. Yeah, it's going to be the summation of that x into f of x, So in this case, it's going to be that column multiplied by that column, and then we get that value, and then we're going to have, so if you do the summation over the entire data, then we have, so this is going to be the expected value. So that means on any given day, without any other information, we expect to sell 1.5. We expect to sell 1.5 cars if no other information is provided. So that means in 2 days we expect to sell three cars, and so on and so forth. So this is how you use this given the previous information that you had. Notice this is different from, because remember, the probability of the entire distribution is going to be equal to 1, yeah. But this is the expected. This is the expected value, and this is very similar. If you are paying attention, this is very similar to how we are computing. Do you see the formula are very similar to the formula that we use for grouped means, grouped averages? So there's some similarities, not exactly the same formula, because for instance we are not dividing by n, yeah. But we do not need to divide by n, because this has already been, this column over here, we obtain it by getting the value, the actual frequency, and dividing it by n, yeah. So this is essentially the same formula that we had when we were computing the mean for a grouped frequency for group data. So this formula over here is essentially the formula that you had for computing the mean for grouped data, if you remember, from the previous chapter. So similarly, if you're computing the standard deviation, so this is essentially the mean, and you can see they're still using mu in the notation. So if you look at the variance, it's going to be essentially the same formula, because the variance you have for group data, you had the midpoint. So you had the midpoint, and then that midpoint you subtract. So it's basically going to be the 1.5 minus that value. So it's going to be 1.5 minus, so it's going to be minus this value, minus this value. So you have this result, yeah. If you go back to the formula, you could just see the formula for the variance. So we have x, yeah, we have x minus mu, yeah. So it's going to be that value, x minus mu, where were we? It's going to be, yes, 1.5 minus the actual value on the day, yeah, minus the actual value on the day. So it is that, yeah. So because you want to see the values, how do they deviate from what was expected, yeah. How do they deviate from what was expected? And of course you're going to square this. So this is first of all you have to get the deviation, then you want to get the square deviations. So the square deviations is basically this into itself, by itself. So you have that, then you want to get the summation of the square deviations. So you're going to have the sum so after you get the square deviations, you want to have the these square deviations multiplied by the actual frequencies, so it's going to be so this is the square deviation multiplied by the frequency. So you have and then you want to get the summation of this. You want to get the sum of this to get you the standard deviation, right? rather to get you the variance, right? So again, this is very similar to what you do for group data. For group data, usually the x is going to be the midpoint. So in this case, you're taking the x as it is, right? And then you're getting the deviation, as usual, get the square deviation, and then you're getting the sum of the square deviations. So we are not dividing by n. A reason being that this f is already this already a frequency distribution. It is this is a percent frequency distribution. Yeah. So we have already divided by n in this column. Yeah. So essentially, what you're doing is like getting population variance over group data. But in this case, the group is going to be the x. Yeah, it's going to be the proper outcome. So I'm saying a lot of words basically just because I want to relate this particular step with the calculation of the variance for group data. But you could just get the formulae and learn them, which I do not recommend to learn them as separate objects in your head. But yeah, so you basically just get this formula. And if you want to calculate the standard deviation, it's going to be very easy. It's going to be the square root of this. So the standard deviation, as usual, is going to be the square root. So that's the square root function, square root of this, and to give us a value. So this will give you the deviation. It gives you a deviation of that random variable. Yeah, so you are computing the deviation of that random variable because there's a value you expect, but it's not necessarily going to be that value. So there's going to be a bit of standard deviation. So if you just go back to the slide, so this was a Decalo Motors example. So that was the variance for a discrete probability, for a discrete probability distribution. And we also, just to recap, we also did cover the uniform probability distribution. We also did cover the uniform probability distribution. So that basically ends this particular section.